Good day once again. Welcome to today's class on radiopharmaceuticals. Yes, this is a topic from radioactivity, so to speak. So in today's video, you will learn a lot of things about radiopharmaceuticals. What are radiopharmaceuticals? Radiopharmaceuticals are materials or substances which are used either in the treatment or for diagnosis of malignant cancers. When we talk about malignant cancers, we say they are cancers that are not what? Localized. They spread around the whole body. And so one of the drugs that are used in treatment of such cancer is called radiopharmaceuticals. Drugs like radon and all have you. And so in today's video, we want to discuss these radiopharmaceuticals, so to speak. That means that these radiopharmaceuticals operate or function with principles of radioactivity. Yes, they undergo what we call radioactive decay. And so, in the process of radioactivity, because they are unstable substances or unstable elements or unstable drugs, they disintegrate or undergoes changes so as to obtain a stable state of it and also reduce what we call radiations. These radiations can be alpha radiation or alpha ray, beta radiation, beta ray, gamma radiation, gamma ray, and so on. And so, we want to look into that topic in full, and it's important to note that the units of radioactivity is called becquerel. Becquerel is a unit of radioactivity. This is because the scientist who discovered this topic radioactivity is called Henry Becquerel, okay, in the year 1896. And so the units now take up his name, becquerel. Other units of radioactivities we have are curie, millicurie, and so on. This becquerel, you can also see kilobecquerel, you can also see gigabecquerel, you can also see megabecquerel, and so on. So we have other units of becquerel, other units of it, but the number one unit of it is becquerel. So other subunit of it, we also have it. Now, it's important for us to note some important formulas when it comes to radiopharmaceuticals. We need to know some important formulas. First of all, for you to know this formula, we need to recall that since radiopharmaceuticals comes from the topic radioactivity, okay, that radioactivity is one of the processes that undergoes first order reaction equation law, and that is radioactivity undergoes or obeys first order reaction equation. And so we say that since it undergoes first order reaction equation, it will obey this rule: LC equals to LC O minus KT. It has to obey this equation. That is what we are saying, that radioactivity obeys first order reaction equation. That means this equation, the graph goes this way. You are plotting the graph of length t against what? Time. Okay? And it will go like this. It will give you a negative slope, which we call minus what? K. Is a negative slope. When you go to the topic chemical kinetics we posted on our channel, you will see how we discuss all the orders of what? Orders of reaction we have. Okay? Zero order, first order, second order. You see how we discuss them in full. And so this is the intercept, where we call it, the intercept is called lane CO, lane of the initial concentration. The CO means initial concentration. And so if this is equal to x, if that intercept is equal to x, it means that lane CO is equal to what? X. Lane CO is equal to x, and therefore CO will be equal to opposite of lane is exponential raised to the power of x. That will be how to deduce the value of initial concentration from the graph. And so we said radioactivity or radiopharmaceutical products obeys first order reaction equation, and so it will go this way. From first order reaction equation, we noted that half-life of a first order reaction equation is CT. Half-life simply means the time it will take 50% of that radiopharmaceutical product to decay. Yes, or the time it will take that radiopharmaceutical product to decay to its half. And so CT decaying to its half initial concentration declaring to itself, it means that Ct will be equal to 0.5 CO. And so when you put it here, you say that ln 0.5 CO equals to ln CO minus KT half, because you are talking about half-life. This K is called rate constant. The rate constant or the decay constant of that first order reaction equation. And so what we now say here is applying principles of logarithm here, because ln mean log, but they are not exactly the same, but they are related. This coming here, we have ln 0.5 CO minus ln CO equals to minus KT half. Okay? And so we now say subtraction law of logarithm will come in. 0.5 CO all over CO equals to minus KT half. This will cancel this. Ln 0.5 is equal to minus KT half. Therefore, the half-life will be equal to ln 0.5 all over minus K. Now, if you press it in your calculator, ln 0.5 will be giving you minus 0.693. And so you say that half-life is equal to minus 0.693 all over minus K. Minus will cancel minus. So that means half-life of any radiopharmaceuticals is said to be 0.693 over K. Okay? Then this is for half-life of it. If you are asked to get the half-life, they have to give you the what? The decay constant. Are you getting it? So you just compute 0.693 over K. You get the half-life. Another formula we also need to recall to ourselves is mean life of a radioactive element. Another formula we shouldn't forget is mean life of radiopharmaceuticals products. What is the mean life? Mean life is equal to half-life all over 0.693, and that will be giving you 1.44 half-life, because inverse of 0.693 is 1.44 half-life. So anytime they ask you to get the mean life, just check 1.44 times the half-life given to you. Okay? Another formula we should not forget is Ct equals to CO exponential minus KT, where the E is equal to 2.718. That is equivalence of A in a calculator. Remember, this K I've been writing here, it varies. You can call it K, or you can call it what? Lambda. You can call it any letter you want, but whichever letter you put there, know that it represents what? The decay constant. Okay? Now, this formula you see here is equivalent to Ct equal to CO bracket 0.5 raised to the power of T over half-life. What does this two formula mean? If you are asked to get the concentration of or amount of a particular radiopharmaceuticals which remain at a particular time, you remember, if I'm a radioactive element or radiopharmaceutical element, or if this is a radiopharmaceutical element, so to speak, the half-life we just mentioned simply mean if the half-life of this is 10 days, it means when it gets to 10 days, half of it will decay, half will remain. Right? Now, that means if you get to another 10 days, the remaining half will also decay. Then half of it will remain. Are you getting it? And so, question is, if the half-life is 10 days, how many of it will decay when it is 2 days? You will notice that if this is a full pharmaceutical product, the implication is that if the half-life is 10 days, on 2 days, it could be something here that will decay. Just small portion of it will decay. That means not up to half of it will decay. So if you want to know amount that will remain if it decay small in 2 days, if you want to know the amount that remains, you use CT equals to this or CT equals to this. Then if it decays to half, I want to know the amount that decay. That is, you want to know amount that decay and amount that remain. You still use that what? Same formula. So this formula is telling you amount remaining or concentration remaining. Amount remaining or concentration that what? Remain. Concentration remaining or amount remaining. Concentration remaining or amount remaining. Then if you are asked to know or to get the value of amount that decay or the concentration of that radiopharmaceutical that decayed, what you say is initial concentration minus what you have here, CO minus amount remaining equals to concentration that decayed. So if you want to get the concentration that decayed or the amount that decayed, you see the total concentration, which is the initial concentration, minus CT. And you must have gotten your CT or the amount remaining using any of these two formulas. So you have to subtract it so as to get the concentration that decayed. So please have this in your mind as we run down these questions on the board. Okay, let's see. It is also important to note that 1 becquerel is equals to 2.7 times 10 raised to power minus 11 curie. Then that is about 1 becquerel. If you want to get 1 kilo becquerel, 1 kilo becquerel means multiply this by 1000. That will be giving you 2.7 times 10 raised to power of minus 8 curie. Then 1 mega becquerel is equals to 2.7 times 10 raised to power of minus 5 coulomb. And 1 giga becquerel is equal to 2.7 times 10 raised to power minus 2 coulomb. It's important to note all these conversions, okay, as we go about to solve this, okay. And so if you are talking about 1 millicurie, 1 millicurie simply means 10 raised to power minus 3 coulomb. 1 millicurie is equal to 10 raised to power minus 3 coulomb. Then 1 microcurie is equal to 10 raised to power minus 6 what? Curie. So like that, you have to note all these conversions. They are very important. Let's see how to solve all these problems we have on the board. 1. If the half-life of a radioisotope is 13.3 hours, calculate the mean life of the isotope. Solution. Okay, let's see how to solve this problem on radiopharmaceuticals we have on the board. 1. If the half-life of a radioisotope is 13.3 hours, calculate the mean life of the isotope. Tell them that mean life of the isotope denoted with 1 over this or 1 over lambda is equals to 1.44 times half-life. And what is 1.44 times half? What is half-life? 13.3. 1.44 times 13.3. And that will be giving you, when you press this in your calculator, 1.44 times 13.3 to be giving you 19.152 hours. So the mean life is also in hours, 19.152 hours. So try to use your calculator to cross-check it and know if I am correct or if I am not correct. Okay? Question number 2. So as you use your calculator to check it out if I'm correct or not, use the comment box below and tell me yes, I am correct or I am wrong at a particular point in this calculation. Okay? Then number 2, if 100 milligram of iodine 131 labeled albumin contains 150 milligram of millicurie, what is its specific activity? Now, we had a formula on specific activity. We said that specific activity is quantity of radioisotope. Quantity of radioisotope all over the activity of the radioisotope. So quantity of radioisotope all over the activity of the radioisotope. Okay. Then the quantity is if 100 milligram of iodine 131. This is the quantity. Labeled albumin contains this. That means this is the activity or the potency of that what radioisotope. So we say the quantity is 100 all over the what? Potency 150. 5 here, 2, 5 here, 3. That will be giving you 0.667. That is the what? The specific activity of that radioisotope. Okay? Then we go to question number 3. The half-life of a radioisotope is 2.5 days. Calculate the disintegration constant. We noted that half-life is equal to 0.693 all over K. That is decay constant or disintegration constant. We now say it implies that disintegration constant, this will come up and this will come down. 0.693 all over. What is the half-life given to you? 2.5 days. 2.5 days. And so you have to use your calculator and what? Solve it. You'll be getting 0.2772 per day. Now to solve question number 4. To solve question, the original quantity of radioisotope is given as this. So we say CO is equal to 500 microcurie. If the quantity remaining after 16 days is, okay, quantity remaining, we'll call it CT, equals to 125 microcurie. Your after what? 16 days. So after 16 days, calculate the decay constant and half-life. We recall that we had this formula equals to CO exponential minus KT, right? Right. Now, because they asked us to get our half-life and the decay constant, see what we say. We tell them that the decay constant K is equals to ln CO over CT all over what? Time. We have made this subject of formula from what? From this formula. Ln CO over CT all over T, time. Okay? One can also say that this K is equals to 2.303 all over time log what? CO over what? CT. Depends. CO over CT. That will tell you that 2.303 log is equivalent to ln. Then CO over CT all over time. So they are the same thing. Okay? So see what we get now. Ln K is equals to ln bracket 500 over what? 125 all over dt is what? 16. And so in your calculator you have what we call ln. You just press ln bracket 500 over 125 all over 16. It will be giving you 0.086636 per what? Is in days per day. Per days. Per day. So what we now have here is K is 0.086636 per day. Okay? And so recall that your half-life is equal to 0.693 over what? K. And therefore, half-life will be equal, because they say we should get the decay constant, which is this. This is your decay constant. Then for half-life, 0.693 all over your K is 0.086636. Why we use a longer number is because we are still going to get half-life. This is not end of the question they asked us. They asked us to get K and we are still going to use the K. So if we just approximate it, just maybe 0.87, it will affect the value of half-life we'll be getting. Maybe higher, too high or too low. And so when you compute this in your calculator, it will be giving you 7.99. So approximately is what? 8 days. So the disintegration constant or the decay constant is 0.086636 per day. Then the half-life is what? This over this. That is 8 days. Please try to what? Make use of your calculator very well. If there is any arithmetic we did here and you don't understand, please use your comment box and what? Bear up your mind. Tell us where the error came from so that we'll help you out on that. Question number 5. A sample of iodine 131 has initial activity of 30 microcurie. If its half-life is 8.08 days, calculate it. So has initial, we say CO is what? 30 microcurie. and its half-life is equal to 8.08 days. Calculate its activity in microcurie at exactly 20 days. Oh, get your what? CT at exactly what? 20 what days. You now recall that there are many formulas one can use here. You can use CT equal to CO bracket exponent minus KT. When you are using this, you have to get your decay constant. Or you can use CT equal to CO bracket 1 over 2 T raised to the power of half-life. Now, since they gave you the T, they gave you the half-life, you can use this one. You now say that your CT is equals to the initial ohm, which is 30 bracket 0.5 raised to power. What is your small t? 20. And what is your half-life? 8.08. So what you do, you use your calculator and say 20 over 8.08. Whatever it gives you, you say 0.5 raised to power of that number, then times 30. Okay? So your CT will be equal to 5.399 microwatt curie. That is if you use this method. Then if you are using this method, you tell them that your CT is equal to, this is what? 30 bracket, this is 2.718 raised to the power of minus your K. What is your K? 0.693 all over half-life, which is 8.08. Are you getting it? So your K is 0.693 all over 8.08. Then times your small t. Your small t is 20. Once you compute this, note that when you compute this, you have 0.693 times 20 all over 8.08. It will be giving you 1.71535. That is what this will give you. Are you getting it? Once you compute it. So your CT will be equal to 30 bracket 2.718 raised power minus 1.713,715,35. And when you finish computing this, that will be giving you 5.399 microcurie. Okay? And so what you do is you try to use your words, use your calculator to confirm these answers. This is the first method, and which other one? This is the second method. Go to the last question on the page. The vial of sodium phosphate solution has a labeled action of this. How many ml of the solution should be administered exactly 10 days after the original assay to provide an activity of this? Okay, your CO is equal to 500 microcurie per ml. Okay. Now, your small t is 10 days. And your half-life is what? 14.3 days. We are looking for our CT. That means that this time it's not up to the half-life. We want to see how many will decay when it gets to 10 days and how many will remain when it gets to 10 days. So how many that will remain is what we call CT. We said to get how many that will remain, we say CT equals to CO. CO, then exponential minus KT. Where K is equals to what? 0.693 all over half-life 14.3. Are you getting it? So CT equals to 500 2.718 raised power minus 0.693 all over 14.3 times what? 10. That is your T. All are the power. So when you sort out this with your calculator, this times 10 is 6.93 all over 14.3. Whatever it gives you, get 2.718 or raise to the power of that number, negative of that number. Are you getting it? So when you say 500, so what you do is that you simplify this. 0.693 times 10 all over 14.3. That will be giving you 6.93 all over 14.3. Sort it out. Then 2.718 raised to the power minus that answer. Use your calculator to sort it out. Don't worry your head on that. So when you sort out this power, that is this times this, it will be giving you 6.93 all over 14.3. When you sort it out, when you divide it, it will be giving you 0.48462. 0.48462. We are using a longer digit because we still need it here. And so you'll be having that your CT is equal to 500 2.718 raised power minus 0.48462. This will be giving you this raised power this with your calculator times this. That will be giving you 307.9825. 307.98 microcurie per mil. Since the initial concentration is in microcurie per mil, final concentration will be in microcurie per mil. Now to get the mil one should pipette from this in 10 days, which will be equivalent to 250 microcurie. Following radioactivity principle, you just say that this is in 1 mil. Say 307.9825 microcurie is equivalent to what? 1 mil. Okay? And so you now say 250 microcurie will be equals to what? What you now do is this, if you approximate this, you will be having this times is 250 microcurie per times mil all over. This is about 307.983. That is approximation. So you will be having it as 250 divided by 307.983. That will be giving me 0.8117 per mil, because this is a microcurie and they will cancel out, leaving you the mil. So that is the solution to this question. You will see more videos on our channel. Please don't forget to click like and subscribe if you enjoyed the video.